The following is an original production of AZPM News.
Arizona Science is supported by Research Corporation for Science Advancement.
For Arizona Public Media, I'm Leslie Tolbert, Regent's Professor Emerita in Neuroscience at the University of Arizona, and this is Arizona Science. Our guest today is Maya Kaelberer, Department of Physiology in our College of Medicine. She recently won a very prestigious New Innovator Award from the National Institutes of Health for her research, and I'm excited to talk with you today. Thanks for joining us.
Thanks so much for having me.
Tell us a bit about your background before we get to what your current research is. What led you to study the details of how our brain and gut communicate with each other?
That's a great question. So I am a sensory neurobiologist by training. So I started out being really interested in how it is that we take the physical world and how is the physical world then interpreted by our central nervous system. Because in the end, really what it is that we perceive is really a filtering that our senses are doing. And so when you think about how it is that you're seeing things or how you're hearing things, all of this has to be processed first by these sensory transduction cells. And so my interest in the gut-brain connection was really about this is almost like the frontier in sensory neurobiology, because we know almost nothing about how it is that our gut is transducing signals, even though food and how our gut feelings work is the essence of who we are.
What do you mean by gut?
So when I'm talking about the gut, I'm specifically talking about the small intestine and the colon.
And you've now discovered a set of cells in the gut that it sounds like hadn't been described before, that you're calling neuropod cells. Tell us how you discovered them and then what it is you think these cells are doing.
Yeah, so I discovered these cells during my postdoctoral work. And the idea here is that there are these gut sensory cells, but they were classically known to be hormonal. And so they release a lot of the satiety hormones that we're used to hearing about. I now can say GLP-1 is one of the main ones. We've all heard of Ozempic. And they release a lot of these hormones that make us feel full. But they're a sensory cell. And so we were thinking, well, there must be some kind of direct communication between the nervous system and these cells. They can't just be doing this indirect communication because all of our other sensory systems have this direct communication. And so we went about trying to prove that that there was a direct synapse between these neuropod cells and the nervous system.
And a synapse is where one cell talks to another.
Yep. You could think about it as like a direct synaptic communication would be like you and I talking. You can interrupt me and say, hey, tell me again what this synapse means, and we can communicate, and we can pass a lot of information to each other. And you could think of a hormonal communication more as like, I got this flyer in my mail, and you don't necessarily need to respond to it, but it's a signal that gets sent out to everybody.
So you found these cells. They have an interesting morphology, an interesting shape, an interesting position in the intestinal wall. And you're finding that they may have really interesting functions. Take us through from ingestion of food to what you think is happening in these cells, and then what you expect is the outcome of having these cells.
Yeah, so I'm going to take you on a journey of sugar, because we love sugar. And so we love sugar so much that we have artificial sweeteners to try and prevent us from eating too much sugar. And then, so there was this paradigm. We have these nutritive sugar and we have these artificial sweeteners. And we thought artificial sweeteners are going to cure obesity. Once we figured it out, we're just not going to eat high calorie sugar anymore. But it turns out this didn't happen. And what we know from the literature is that if you give an animal the option between a real sugar and an artificial sweetener, and they're both the same sweetness, the animal will always drink the real sugar over the artificial sweetener. And this is true if you get rid of taste in the tongue and you just go directly into the gut. And what we found is that these neuropod cells in our gut are actually using two different receptors to distinguish between the real sugar and the artificial sweetener. And then they're releasing two different signals.
Aha.
And the signal for the real sugar drives our consumption of that. So if we block the cell or we block the signal, we get rid of that preference for the real sugar over artificial sweetener.
And you can block one or the other of these receptors?
Yeah, so we could do that using kind of some, what we like to call it, genetic gymnastics in our various animal models. So like, what does that mean to us? So for me, this really made sense because I like artificial sweetener in my coffee. And I've heard this a lot, like, oh, but I like Diet Coke. And that's fine. We have a frontal lobe that helps interpret these signals. But I like artificial sweetener because artificial sweetener to me is lighter in my coffee. And I'm getting my coffee in the morning and I want to get up and I want to go. And the sugar to me just feels heavier. And so I think what the signal is telling us, and if we're paying attention to what our gut sense is telling us, is like how gratifying or how satisfying is that nutrient that you just ingested? And what value does it have?
So these cells are transducing a chemical signal from food into a hormonal signal that then reaches the brain in some way to affect our behavior.
Actually, I would say there are two things. There's the hormonal, so that was the indirect communication. And then there's the neurotransmission. That was the fast, really rapid, in milliseconds. And what's really cool about these cells is they're sending both signals. And that rapid communication is driving you to consume something. It's saying, hey, eat this. But then that slower signal builds up almost, and it builds up to induce what we call satiety, or this feeling of fullness. So within this single cell, we're both getting the drive to consume something, and we're getting the information of when it's enough, when you've had enough, and you should now stop eating.
What are the consequences of this kind of signaling?
The consequences, I think, are a couple-fold, and I can see this going in different directions. I just gave you an example of how you could interpret some of the signals that we're getting from our gut. And they tell us things like, did that hit the spot? Was that really good? You might notice now when you go and eat your next meal, that protein might have had a more gratifying feeling to it. Like sometimes we don't just want cake, we love our vegetables. And it's not quite like, oh, it's rewarding, like it's rewarding sugar on the tongue. It's this different feeling that we have. And if we learn to listen to those feelings, then maybe we could learn to better make food decisions because we know what that signal is actually telling us about the food.
And the signal also is telling the brain and hormonal systems about hormones to release in response to the particular foods we're eating. Is that right?
Yeah, absolutely. And there are different hormones that get released preferentially for certain foods. A lot of the times fat and sugar are very reward-driving nutrients that we have. Protein, though, seems to be more of like a survival-driving nutrient. And what we haven't even talked about, you can't be in the gut world and not talk about it, is your microbiome, right? Mm-hmm. We have a resident microbiome. And we've also shown that these neuropod cells are also interpreting some of those signals too.
Remind us what the microbiome is.
The microbiome is this group of microbes that are living within your gut. And they help us in a lot of ways. But they live there and they help us digest a lot of foods. Sometimes they interact with medicines in order to release different metabolites. And we have this mutualistic relationship with these resident microbes that are living in our gut.
These cells sound very interesting. And you now have a brand new grant that is going to fund research to explore how the foods that a mother eats during pregnancy may create long-term nutritional memories of a sort in her developing baby that then influence how the infant will feel about different kinds of food?
Yeah, absolutely. So we looked at this, we're like, all right, that's got the synapse, we're good, they're here, it's sensing nutrients, it's sensing microbes. And there was this question. The gut surface is an epithelial layer. It's an epithelial layer like our skin is an epithelial layer. And that means that it turns over. What is it, like something like every 7 days you have a new skin or something like that. We're constantly turning over these cells, and we're doing that in our gut surface as well. But it turns out that these neuropod cells live longer than that regular turnover rate. And there's a sparse population that can live out to a quarter of the life of the animal. And what I found actually is then if you go and look in development, when they appear embryonically, they all appear at the same time. So instead of them kind of growing, increasing in numbers as the intestine gets larger and larger, they all appear. And then they start turning over when the animal starts making food decisions, so when it comes off of its mother's milk. This is an opportunity for the mother to encode these sensory cells, these neuropod cells, embryonically, and then help inform the offspring when it goes to make food decisions. It's not just entering the wild west of food. It's entering a world where it has been predisposed to like certain foods that the mother has already told it it's safe. And we see some of this actually in humans.
Another aspect of your work is that this may help you to look into novel ways to treat lots of eating disorders. Tell us about that.
Yeah, so if we know that these cells are now encoding some kind of this nutritional memory, now we can focus on targeting them. Let's say that they weren't quite programmed in the right way, or like people who seem to be really resistant to diets, or like the yo-yo dieting kind of effect. We now suddenly have some biological basis for like, okay, how can we reprogram these cells so that not only are they getting used to what we consider a healthy diet, but they're also allowing the person to feel just as satisfied by that healthy diet as they did with those high-fat, high-sugar diets.
And how do you imagine that kind of reprogramming?
So I would imagine that reprogramming would come either by targeting the cells, or there's a second aspect of this that I didn't quite mention, which is once the cells start turning over, they turn over every about 30 days, every 1 month. And so if we could put you on a diet, and I think that this is true because they say habit takes 30 days, right? If you're on a diet for 30 days, then suddenly as you eat more healthy food, you feel better about eating more healthy food.
So these neuropod cells are our craving cells in a way.
Yeah.
Well, this is absolutely fascinating. Thank you so much for telling us about your research.
Of course. Thanks so much for having me. You could tell I'm really excited about my work, and I'm always interested to hear the next meal you have. Tell me, like, how does your gut feel about it?
Maya Kaelberer is an assistant professor in physiology and a member of UA's Bio5 Institute. You can listen to this and all Arizona Science conversations at azpm.org/Arizona Science. I'm Leslie Tolbert.
Thank you to Research Corporation for Science Advancement for their support of Arizona Science.
This has been an original production of AZPM News.